the house problem. In this video, we are going to set up the system of equations that we need to solve this problem. So let's say a house for cooling purposes consists of two zones, the attic zone, which we labeled with A, and the living zone, which we labeled with B. The living area is cooled by a two-tone air conditioning unit, this one, that removes 24,000 BTU per hour. The time constant for heat transfer between zone A and outside, so zone A and outside, this is the outside, right? It's 2 hours, that's the time constant. The time constant between zone B and outside, it's 4 hours. And between the attic and the living area, it's 4 hours. If the outside temperature stays at 100 degrees Fahrenheit, how warm does it eventually get in the attic zone A? So how are we going to set up the system of equations? So first of all, let's remember Newton's law of cooling. Which says the derivative of temperature with respect to time, the rate of change in temperature, is equal to K times M minus T, where K is a constant. So, in our case, dx dt, let's say again, the x, let's call it x of t. X of t is the temperature in zone B, and y of t is the temperature in zone A. So the rate of change of temperature dx dt in zone B, it's equal to K1, the constant for first one, times the temperature between the medium, the outside, so it's 100, minus x, plus, so here is the x of t, is the change between the house and the outside, and now we are adding the change between the inside and the attic. So it's K2 times y minus x. So this, what we wrote here, is the rate of change of the temperature in zone B with the outside and with zone A. So dx dt, it's equal to K1, it's with the outside, so K1 it's 1 over 4 is the constant, so it's 1 over 4, 100 minus x, plus K2 it's the change with the attic, so it's 1 over 4 y minus x. So this is one of the equations that we are going to have to remember. So it's the temperature exchange with the outside and with the attic. Now let's take a look at the zone A. So zone A, it's the attic. So dy dt. Now the attic exchanges temperature with the outside and with the inside. So it's going to be with the inside, with the B, the temperature, it's the time constant, it's 4, so then 1 over 4 times, and now the change with the attic, so it's going to be x minus y, the change between the attic and the house, plus, and now the change between the attic and the outside, it's 1 over 2, and then outside it's 100 degrees minus the attic, which is y. So this is the rate of change of the temperature in zone A. So these are the two equations. Now there is one more information which tells us that the living area is cooled by a 2-ton, I think it's just tone like that, AC unit that removes 24 BTU per hour. So that information, right, it's in the living area. In the living area, it's B. So our XT here, we have a little bit more heat removed. So then we are going to have to subtract. And what are we going to subtract? Well, this removes at 1/2 degrees Fahrenheit per 1000 BTU. That's 1/2 times 24. That's 12. So basically, the AC removes heat at a rate of 12 degrees Fahrenheit per hour. This is removed from B. So then here we have minus 12. So the actual system is going to be this dx dt equals 25 minus 1/4x plus 1/4y minus 1/4x minus 12, and dy dt equals 1/4x minus 1/4y plus 50 minus 1/2y. So here we can actually get dx over dt equals 25 minus 12, that's 13. This 2 is minus 1/2x plus 1/4y, and dy dt equals 50 minus plus 1/4x, and then these two together are minus 3/4y. Or we can multiply it by 4 to get rid of the denominators. So we have 4 dx dt equals 52 minus 2x plus y, and 4 dy dt equals 200 plus x minus 3y. So this one, we learned that we can use operators. So it's 4d plus 2 applied to x minus y equals 52, and then minus x plus 4d plus 3 applied to y equals 200. So this is a system of equations, and because it says how warm does it eventually get in attic zone A, it means we need to solve for y. So you don't have to solve this system for both, you have to solve for y.